I got a brief nap before lunch, so I'm in good shape this afternoon. And mentioning lunch, over lunch I was told that I tell dad jokes. But that's not the worst part. They had to explain to me what that meant. So it made sense once they told me. I get it now. But, as I said last night, I think I used to be cool, but that was a long time ago. I don't know what happened to me. But you'll get your turn. Just wait a while, all right? It'll happen. We could put that on part of the curse and part of the whole thing, but I think that goes beyond that a little bit. Anyway, I want to talk today about the evidence that the world is young, and I kind of overlap a little bit with what I said this morning. Again, there were two explanations of how we got here. One of them is evolution. And I define that as a purely natural, purely physical process, and the contrast to that is creation, which is a supernatural process. But again, I want to be very specific. I'm talking about the God of the Bible, not talking about any other gods involved with this. And again, I addressed the question this morning, is it important what you believe about this? And I think most of you agreed with me, as I showed you, yeah, it is important because it does change your worldview. If you have an evolutionary worldview, it's going to cause you to look at the world very differently than if you have a creationary worldview. It's a person who's a Christian who has an evolutionary worldview is really confused. They're mixed because they've got so much of the world in their thinking, and they shouldn't do that. They should be heavenly minded and biblically minded about these things. And one of the things that gets kind of wrapped up into this, and a question that comes up very quickly on this whole issue of creation or evolution, is a matter of time. According to the consensus you generally get in television programs and in classes and in textbooks and so forth, is that the world began 13.8 billion years ago in a Big Bang. And then after 9 billion years or more, the solar system finally formed, and the Earth formed during that time. And then life appeared maybe 500 million years later, about 3.5 to 4 billion years ago. And not much happened for the next 3 or 4 billion years until about 500 million years ago, life began to take off, what we call the Cambrian explosion. And over the next 500 million years, a lot happened. In the last million years or so, people appeared. That's, in a nutshell, what the time frame is. That is very different from what you find in the first few chapters of Genesis, is it not? And trying to get those two together is, well, it's impossible because they don't mix very well at all. Now, why do so many scientists and why do so many evolutionists believe in billions of years? And I am thoroughly convinced, after years of cogitating on this and studying this, I am convinced it's because of the assumption of evolution. Most people seem to think, well, it's a matter of scientists just going out and just doing experiments, doing observations, and they're just inexorably led to the conclusion that's where the data took them. That's just the way the world works. As if the scientists simply had no preconceptions, no presuppositions, that's just where the facts led them. And that's not the way it works, because I've known too many scientists. All right? Scientists, we're like anybody else. We have biases. And most of them will pretend. In fact, if someone tries to tell you they don't have any biases, hang on to your wallet and back quickly far away from you can, as quickly as you can from that person, because they're trying to sell you something or take something. Everybody has a bias. I think by being here and hearing me speak, you got some of an idea what my biases are. Yeah, I am biased towards the Word of God in this, and I think all of you are as well. Bias is not that bad of a thing, really, as long as you're biased about the right things. That's the important part here. But if you're biased towards believing in naturalism, of course you're going to believe in billions of years. So it's no surprise that your work then leads you to that conclusion. You kind of go in a circle. You assume billions of years, you get there. Why is that? Well, because evolution requires billions of years. You don't see new organisms popping into existence. You don't see mountain ranges suddenly appearing. You don't see stars being born. You don't see a lot of things that evolutionists tell you must have happened. So consequently, if you don't notice it taking place, it must happen incredibly slowly. Not even a glacial pace. It's much slower than that. And so you don't notice it over many, many lifetimes, certainly not over one lifetime. But on the other hand, creation is fast. And I'll give you two reasons why I believe creation was fast. Number one, there's no need for great time. God speaks into existence it's there. Why would God take billions of years to do something when he can do it instantly or nearly instantly? Certainly 6 days is pretty fast compared to billions of years. But even more specifically, the Bible pretty well declares it was done in 6 days. And those days, there are many textual arguments why those are 6 normal days. People try to say, well, maybe they were long periods of time. Again, that's not my subject I want to talk about today. Other people have addressed this before me and done a very good job on it. But suffice it to say, there are many textual reasons for believing that those are normal days like we experience today. And so consequently, the age issue ought to be a discriminator between creation and evolutionary worldview. If the world has come about through evolutionary processes, then there must be evidence of billions of years. If, however, that the world is a result of fiat creation from the book of Genesis, then there might be evidence that the world is much younger than that. And so as a creation scientist, part of my job is to try to identify things out there that might indicate recent age. So I would entitle this little discussion, Thousands or Billions of Years. And I've come to the conclusion over my decades now of study that it has very little to do with physical evidence. It has everything with your assumptions and your worldview. You assume the world is billions of years old. You're going to find evidence that it's billions of years old. But if you start with the assumption it's only thousands of years old, guess what? You're going to find evidence that it's only thousands of years old, certainly less than billions of years. And let me give you an example of one of the examples from the past of why and how evidence has little to do with it. In the late 19th century, I'm talking like by the 1880s, 1890s, most biologists and geologists thought that the world was at least 100 million years old. Now, as it turns out, that's a lowball figure by most estimates today, but that was their minimum figure they had. Now, did they have any evidence for that? No, there was no evidence whatsoever for this. What they were relying upon was the assumption of evolutionists. Biologists at that time looked at the diversity of organisms. They said, we need at least 100 million years to explain the diversity of organisms we have. And the geologists looked at landforms and said, we need at least 100 million years to get the diversity of landforms that we see. And so they all converged on this minimum figure of 100 million years. But then Lord Kelvin came upon the scene, William Thomson, a.k.a. Lord Kelvin. By the way, he was one of the last photographs in that montage of Think Different. All right, I recognized him. Anybody else recognize Kelvin besides me? All right, he was one of the greatest physicists of the 19th century, died in the early 20th century as an old man. But he literally wrote the book on thermodynamics. He knew more about it than anybody did. And he also addressed a number of issues. And what Lord Kelvin did is he gave 2 good evidences that the sun and the earth, either one of them was no more than 30 million, maybe 20 million, but no more than 30 million years old. Now, his work has been largely supplanted now with new discoveries. That's not my point. I point this out to people, and they say, well, wait a minute, we've shown how his work was in error. Yeah, but the problem was in 1890, people didn't know that. He gave 2 devastating arguments. He said the sun can be no more than 20 to 30 million years old. The earth can be no more than 20 to 30 million years old. And the evolutionists at the time, the biologists and the geologists, what was their response? They basically shrugged. They did not have an answer for Lord Kelvin. Were they convinced that Kelvin was right? No. They had good, hard evidence that disproved their argument for 100 million years minimum figure. And yet they threw that completely away, not because there was anything wrong with the data at the time or the argument that he used at the time, but merely because it didn't conform with their worldview. So people today want to talk about radiometric dating. I'm not impressed with radiometric dating for the most part, by the way. And they try to argue, well, that's the evidence we have for the antiquity of the earth. And no, that's not it. They believe the earth was very old long before anybody invented radiometric dating. So radiometric dating has almost nothing to do with it. It came along very much after everyone decided how old the world really was. So that's just an example of the past like this on all of this. A few observations. Again, back in the turn of the last century, belief in old Earth was in spite of, not because of, the best evidence. The best evidence at the end of the 19th, beginning of the 20th century, was that the world was not nearly as old as people thought, yet people rejected that by and large. And again, the great ages we see talked about, the billions of years, is based upon the assumption of evolution. You take away the assumption of evolution, there's absolutely no reason to believe in great age for the world around us. And again, creation does not require great time because it's miraculous, very quickly. Doesn't have to be quick. By the way, people sometimes ask, well, aren't you limiting God? Couldn't have God have taken billions of years to create the world? And the answer is yes, he could have. But you know what? He's revealed his timing in his word. And so you're not taking God seriously at that point. You're not taking his words seriously if you persist in believing in billions of years. So there are really two ways to approach the question. One is to start with the Bible, and the other one was to start with quote-unquote science. I didn't put it in quotes, but I'm putting the air quotes here about this. And this kind of confuses the matter because we talk about two types of science that's involved here, and we get trashed for this, but I think it is still a very good dichotomy between them. We have what's called operational science. That's the science of here and now. It's how we observe the world. We can experiment in the world today. And then we have also historical science. This is or origin science. It's talking about past events. Now, sometimes I hear this argument, this statement made that disbelieving evolution is like disbelieving gravity. Anybody heard that statement before? Yeah. Well, already they've confused the two of them. Evolution is an idea about historical science. We weren't there, you weren't there, so consequently you don't know what happened. You try to piece together what might have happened based upon the evidence you have and your assumptions you make. But the other one, gravity, is an example of operational science. By the way, there are different versions or different views of gravity. What is the dominant theory of gravity today? Anybody know? What's the widely accepted? Shout it out if you got it. What? General relativity, that's exactly right. It was published 100 years ago, and that is the dominant theory today. Now, in most situations, we use Newtonian gravity because it works pretty well, but we believe that it's just a special case of the more general situation of general relativity. By the way, is general relativity likely to be the last word on this? No, there's no theory of quantum gravity. Quantum mechanics and gravity are the two extremes, and you can't really merge the two. So they're looking for a way to put these together. They're trying to put all the basic forces of nature together. If they do that, they might get what's called the grand unified theory and theory of everything, gut and toe for short. And they've been working on it for decades. It's a long way as a way to do that, but it's probably not the final word. But it's a very good theory. By the way, has it been tested? Countless times it's been tested. In fact, we have experiments going on now that are testing between different versions of general relativity. General relativity is not one specific theory. It's actually a general principle, and then there's a suite of different variations within that theme. And so there are experiments going on right now that are trying to distinguish between which ones are likely to be more true than the others. That's the way science is supposed to progress. But you see, you can build an experiment, you can go in the lab, you can do an experiment of general relativity or any other theory of gravity that you wish. But how do you devise a theory of evolution or experiment for that you can test? Well, short of building a time machine, you can't do that, can you? So it's kind of confusing those two, and the principles used in historical science and operational science are very different. Now, they also sometimes will tell us that the Bible is not a science book. How many times you heard that? A bunch of times, right? And you know what? When people tell me that, I agree. I say, yes, the Bible is not a science book. But it is a history book. The first 17 books of the Bible are historical books. You've got the then 5 poetic books. But keep in mind, one of those, Job, is a history book because Job was a real person. And then you go to the 17 prophets in the Old Testament, and how much history do they contain? A bunch. You ever tried going through Jeremiah? It's a little confusing because he jumps around, In the year of whatever of this king, this happened, and then he says, and later on, in the year of this king, and the king was before the last one he just talked about. You can use the timeline, though, if you match it up with the other historical books to figure it out. So really, all but about 4 of the Old Testament books are history. The Gospels are history books. And Acts is a history book, is it not? Already a good deal of the New Testament is history, but you go to the epistles, do they contain some history? Oh, there are all sorts of clues, where Paul was, what he was doing, all these sorts of things. And we can kind of date his ministry at different questions. And I won't even mention Revelation because that's all over the place. Is it history? Is it prophecy? What is it? I don't think anybody really knows all the answers to that. But the point is, the vast majority of the Bible is a history book. And so if you want to practice science without talking about the Bible, stick with operational science, not a whole lot to complain about there. But the moment you start making supposed scientific pronouncements about the history of the world, then there is a problem, because it can run headlong into what the history of the New Testament, the Old Testament says. All right. The length and age of creation, I do believe the creation week was 6 normal days. It's 6 days pretty clearly from Genesis 1, but I think it's also clear from the context those are normal days. And then you can take the chronologies and genealogies, and you add them up, and you get something close to 6,000 years, a little more than 6,000 years. James Ussher, 350, almost 400 years ago now, came up with an age of date of creation of 4004 BC. Can you get that by just adding up all the chronologies? You really can. How he arrived at that 4004 is interesting. I think the date of creation is probably a little closer to 6,200 years rather than 6,000 years. But, what's a couple hundred years and all that? Certainly not millions of years. But we're talking roughly 6, maybe approaching 7, but probably not. And so can we find evidence of all this? And my answer is I think we can. And I'll share with you a few of these today dealing with astronomy. Here we have the Earth pictured. You know that the Earth has a magnetic field. And you may not know what's causing that field, but the theory is down inside the Earth we have the core at the center. And the core is primarily iron and nickel. And the inner portion is solid. The outer portion is liquid. There's a reason for that, kind of inverted from what you might think. But there are probably currents in that liquid portion. By the way, this liquid solid is pretty well established from seismology. Earthquake waves, as they pass through the Earth, we can study those. It's just like, anybody here seen a sonogram before? Who hasn't seen a sonogram, okay? And you can actually identify all sorts of things inside the human body just using sound waves. Well, seismology does the same thing for the Earth. It's a very well-established science. And so this idea of a liquid outer core and an inner core that's solid is pretty well established. The density, I think we can figure that out too, and other properties. It's really a neat science. Well, if it's liquid, it allows for currents to exist in there. The stuff is moving around because it's a liquid. And on top of that, it's iron and nickel are ferromagnetic substances. That is, you put a current in it, you can produce these magnetic fields. And so the theory has been for a very long time that the magnetic field of the Earth is generated by this current inside. Now, if it's produced by a current, a couple things are going to happen. First of all, if you have physical current, it's going to have viscous losses, frictional losses, which will slow down that current. And also, it's going to produce an electrical current. And if you have an electrical current, you have resistance inside of it. And both of those are going to tend to result in the magnetic field of the Earth decaying and diminishing down towards zero. We've been making measurements of the magnetic field of the Earth since the 1830s. So about 180 years we have measurements. Guess what? The Earth's magnetic field is decaying. We have measurements to show that. It's decayed appreciably over the past nearly 2 centuries. So back in the 60s, a man named Barnes, a creationist, back in the 60s and 70s, he showed that the magnetic field is decreasing, tried to fit some curves to it, and he determined that the magnetic field of the Earth was decaying away. And if you continue that into the past, if you go back just like 100,000 years or so, you end up with ridiculously high magnetic fields, ridiculously high currents inside the Earth that cannot be sustained. You go back 500,000 years, and at that point you've got so much motion inside, you basically melt the inside of the Earth at the decay rate we're getting. Strong indication that the Earth's magnetic field is young. Now, later on, another scientist, a friend of mine, Russ Humphreys, took up the mantle, and he started to extend this. He studied the Earth's magnetic field and its behavior over years, and he's also attempted to predict magnetic fields of planets throughout the solar system. He uses a recent six-day creation model to do that, and he was able to predict back 30 years ago the magnetic fields of the planets Uranus and Neptune. Now, the Voyager space probe was on its way to those two planets, and evolutionists had predicted what they thought the magnetic field of Uranus and Neptune ought to be. And Russ Humphreys, before the space probe arrived at these planets, predicted and published what his prediction was based on a recent creation model. Guess whose model predictions were closer to the actual measured values of the magnetic fields? Russ Humphreys were. He actually got them very close to what the actual measured values were, and he made the prediction before they were measured. And again, they try to tell us, well, you creationists, you don't do any science, your model, you doesn't make any predictions. Well, I beg to differ. Russ Humphreys has made a prediction, and his prediction passed. The evolutionary prediction did not pass. And so magnetic fields suggest very strongly of recent origin. Maybe not exactly 6,000 or 7,000 years, but it's usually putting an upper limit, and the upper limit is very small. We're talking 1 million years or less in many cases. Certainly far less than 1 billion years on this. Okay, I showed this photograph earlier, the Earth and the Moon. I want to go in a different direction. I want to discuss this with you here than I did before. You all familiar with the tides? You've been to the ocean, you've seen the tides? Everybody seen that? And you know, the tides rise and fall roughly twice a day. It's actually a little less than twice a day. It's delayed about 50 minutes each day because it's related to the motion of the moon. It's the gravity of the moon acting on the oceans, and it produces a bulge on either side. So if the moon's over here, the Earth is here, you get a bulge here and a bulge there, and the Earth rotates rapidly, and as it does, it takes you through a high to a low, to a high to a low, and back to a high tide again. Meanwhile, the moon's moved forward, so it takes about 50 minutes later on average to do that. Well-established knowledge on that. You go to the coast, pick up a newspaper, they can give you tide tables when high and low tide will occur based on their understanding of their tides. Now, less known is a more subtle effect. That tidal bulge rotates ahead of the line connecting the Earth and the Moon. And that bulge then sitting here, the moon is sitting here, and the moon pulls on this bulge, and it wants to pull the bulge backward like this. The Earth is rotating this way, but the moon's gravity pulls back that direction. So you've got one motion this direction with an acceleration going the other direction. It acts as a brake, and it slows the Earth's rotation down. And that's been measured, by the way. The day is getting longer at a rate of 16 ten-thousandths of a second per century. 16 ten-thousandths of a second per century. That's an amazingly precise measurement, isn't it? And they do that from ancient eclipse records. We can calculate where eclipses would have occurred in the past, and then from historical records, we see where they actually occurred, and we see a difference in longitude as it shifted on the Earth's surface, and from that we can actually compute the tidal interaction. But another thing that's going on is as the, by the way, I'm using tidal evolution. Notice the word evolution using there, just talking about how the Earth and the Moon change over time. In this case, I'm using it in a restricted sort of sense. And as the Earth's rotation slows, the Moon spirals away from the Earth, and we've measured that. The Apollo landings back, late 60s, early 70s, and by the way, we did land on the Moon, despite all those YouTube videos that say otherwise. And they put these special reflectors on the surface of the moon. They're still there after 45 years. And periodically, there's this telescope out at McDonald Observatory in West Texas. They take a big, powerful laser beam. They hook it up to this telescope, and they point it towards the moon. They fire this laser beam. It goes and hits those reflectors, and it comes back. And they check the time difference, like 2 2/3 seconds or 2.5 seconds from the time it left the telescope to the time it comes back, and they divide that light travel time distance by 2, and it gives us the distance to the moon. That's impressive. And what they found is over the last 45 years, the moon is slowly moving away from us at about 4 centimeters per year, about yay much. So in my lifetime, the moon has moved out several times my height. And you may say, well, big deal. What's the big deal about that? Well, they continued to do this. Well, turns out the rate at which it's moving away from us is highly dependent upon the distance. It goes as the inverse sixth power of the distance. Now, if you've ever studied the algebra enough, you know that 1 over r to the sixth power, that's a pretty steep function. And you can then write a differential equation to solve. I've gone through the math myself and checked it. And what we're doing is we're basically taking today's measured rate as a boundary condition on the problem, and you can do the calculation, and you find out that as recently as, actually I got 1.5 billion years old here. It's actually closer to 1.3. But about 1.3 billion years ago, the Earth and the Moon would have been in contact with each other, would have been touching each other. By the way, about 1 billion years ago, the tides on the Earth would have been about a mile high. If you go over on the other side of the mountains, over on the other side of Boone, you would have had beach property twice a day. Forget about living in the Piedmont over there. It's going to be a wash big time. Does anybody believe that tides were ever like that? No. So consequently, that's a problem, isn't it? And it would seem to put a severe upper limit of maybe roughly 1 billion years on the age of the Earth and the Moon. Now, does that prove it's 6,000 or 7,000 years old? Well, no, it doesn't, but it would seem to eliminate anything more than 1 billion years. If you got two choices, 4.5 billion years and 6,000 or 7,000 years, it would seem to eliminate this one, wouldn't it? Now, you can modify what you want to over here, but it seems to me anything over 1 billion years is gone at that point. And again, this is merely an upper limit. This is assuming that the Earth and the Moon were much closer together in the past. I happen to believe that God created the Moon pretty close to where it is now, and in 6,000 or 7,000 years, it hasn't moved very far. Now, I've brought this up. In fact, I was on a program a few years ago. Some of you may have seen it, where I was with several other astronomers who are Christians, but they believe in billions of years, and we're kind of debating this issue. And I brought this very issue up, and their response was that there was the tidal interaction. We happen to be living at an unusually high time of tidal interaction. We have been for a better part of 1 billion years. Prior to that, for 3.5 billion years or so, there was a tidal lock which prevented the thing from the Moon from getting farther away, or from the Earth from spinning any slower. You see, actually modeling how this happens is very difficult. It depends on what's going on in the upper mantle of the Earth. It depends upon the distribution of the continents. We really can't model this very well, but people have tried. They've gone through simulations showing how this might have happened billions of years ago on the Earth. So when these other astronomers pointed it out to me, I asked them, well, where is the evidence for this ever taking place? Give me data. And with a straight face, all of them responded with these simulations. And I said, but simulations are fake data. I mean, you just make up the data when you do simulations, don't you? And when a simulation works, all it means is that the person doing the simulating did a pretty good job. He made the computer program get the results he wanted to get. That's the way it works. And all 5 of these people just sat there and they didn't get it. I mean, they didn't get it. They really thought this was data. I'm very disturbed in astronomy and other sciences too. More and more of the science, quote unquote, is being done by simulation. For instance, there's this big scientific consensus on climate change and global warming, right? Heard all of that? Where's the evidence for it? Man-caused climate change? Well, there isn't any scientific evidence for it. We're only doing the experiment once. You haven't done it twice. We've only done it once. So what are they relying upon? Computer simulations. And sure enough, they've actually programmed their simulations to do exactly what they want them to do. I'm not impressed with that kind of argument. This all comes down to ad hoc. I said yesterday, what does ad hoc mean? It's Latin for we're making it up, right? And it's also called what's special pleading and logic and all of this. And my question is this science? And I think the obvious answer is not. I mean, just because scientists say something, it doesn't make it science, you know? I'm a scientist, and I even give you an opinion on music. But that doesn't make it science, does it? And unfortunately, so many times scientists today give opinions when they're way out of their field and expertise and way out of what science legitimately can do, yet they claim it is. So I'm not convinced of this. I think tidal evolution of the Earth and Moon system actually indicates that the Earth and Moon are far younger than many scientists think. Okay, here we have the photograph of the planet Jupiter. You can tell by the famous red spot on the right side. Over there is a shadow of one of the satellites. It has 4 large satellites, and eclipses happen all the time, right? Frequently enough. I was out at the observatory a few weeks ago with some people, and we saw one satellite pop out. We only saw 2 when we were looking at it. One of them popped out. It took a minute or 2 to brighten up, but it came out from behind the planet. It was being eclipsed in the shadow of the planet. And then we saw one go in front of the planet, and we could see the little shadow like that moving across the face. It was really cool. I had not seen that very often in the past, so it was really neat. Well, we have here one of the satellites of Jupiter. Anybody know the name of this one? Okay, it's spelled Io. It's pronounced Io. And I always get hungry looking at this because it looks like a pizza to me. Look like a pizza to you? Well, I can see some cheese and maybe a little bit of pepperoni. I don't care for mushrooms, but I see them on there. It's a very interesting world, isn't it? And it's got this yellow, orange, and such. Now, the reason why it's got this yellow, orange, and color and reddish coloration on it is because it's covered with a lot of sulfur compounds. Sulfur can actually take on different colors, different compounds that it forms. And why is it covered with sulfur? Well, back in 1979, we first discovered this. There are volcanoes on Io. Here's a little film loop showing an eruption there. Look at the top off the limb of it. You see that little plume up there? That's an eruption taking place. The Voyager space probe saw more than a dozen volcanoes erupting simultaneously. Turns out Io is the most volcanically active body in the solar system, far more active than the Earth is. Now, here on the Earth, volcanic material is typically a molten rock. On Io, it's a little cooler. It's molten sulfur. It's very hot molten sulfur. What is molten hot sulfur, AKA? Anybody know? Nobody knows. It's brimstone. It's brimstone. That's right, Io smells like hell. I'm not cussing, I'm just describing what it smells like, okay? It really smells like brimstone, all right? Because it's got brimstone all over it. And the Galileo probe spent several years orbiting around in the Jovian system, and it took photographs close up of Io, and they could see gross differences in the morphology of certain areas in just 2 years' time. They took photographs, high resolution, came back 2 years later, it looked totally different because it had been completely reworked by this molten sulfur being belched out onto it. Well, as I said, Io is the most volcanically active body in the solar system. The question is, where did the heat come from? Now, one possibility is primordial heat. When these things formed, there could have been heat or formation or heat initially locked up into it. But as it turns out, bodies shed heat over time. They're going to radiate away heat. And that over a few thousand years won't amount to too much. In this case, it's not just radiating it, but it's also blowing stuff out. But you know, over billions of years, Io has had plenty of time. They can run the calculations on it. Io has had plenty of time in order to cool down inside. And if it were really billions of years old, it would be ice cold and solid throughout. So the question is, why is it still hot inside? Well, people said, well, maybe it's being heated by tidal flexing. After all, these things are subject to the very strong gravity of Jupiter. As an object moves around, it's going to be tidally flexed. It's like this, and then it's like that, then it's like this, and it's like this. If you ever take a piece of metal, like a piece of wire, and bend it back and forth, you ever notice it heats up, doesn't it? So this would tidally flex it and heat it up, and that sounded pretty good. And so back in the late 70s, they discovered this problem. They said it's just tidal flexing, and everybody went home, and everybody thought it was just great. Except it doesn't work. There was a creation scientist named Wayne Spencer who's looked into this, gone through the numbers on it, and it simply doesn't work. And in order for tidal flexing to really behave strongly anyway, this thing has to have an elliptical orbit, and it turns out the Io has a very circular orbit. It's almost a perfect circle. And furthermore, it's not inclined much at all to the equator of the planet. It's in almost identically the equatorial plane. There just isn't a whole lot of tidal flexing that you can go on here. And again, we've shown that it doesn't work. So there's still a mystery as to why Io is quite warm inside. Well, it's only a mystery if you believe it's billions of years old. But if you think it's only thousands of years old, it's not a problem at all. And we also found heat in some of the other solar system objects. Enceladus is one of the moons or satellites of Saturn. It too has geyser-like eruptions going on, and a big mystery is why is it still doing that? And again, they say tidal flexing, but again, when you check the details, you find it doesn't work. So you have Saturn. That's one of the what we call the Jovian planets, Jupiter-like planets: Jupiter, Saturn, Uranus, and Neptune. We'll talk about rings here in just a minute. The rings are really cool. Here is the planet Neptune. It's kind of a bluish color. It's got what's called the Great Dark Spot, sort of like the Great Red Spot, except the Great Dark Spot on Neptune. There's something interesting going on with 3 of the Jovian planets. Jupiter, Saturn, and Neptune give off about twice as much energy as they receive from the sun. We can compute how much radiant energy is arriving from the sun. It's going to heat up the cloud tops, and that's going to be re-radiated for the most part. But then we can measure how much heat's being given off. We do that in the infrared, and this has been known for decades. People have measured the output of those 3 planets, and it's about twice the input coming from the sun. Interestingly enough, Uranus is only marginally warmer than giving off marginally more than it's getting from the sun. It's unknown why Uranus is different, but the other 3, it's about 2 to 1. Now, where is that energy coming from? Well, again, you could argue primordial heat, but you can also calculate the rate at which that primordial heat would leak out. And if originally these planets were very hot inside, billions of years ago, they would have cooled off already. So where is the heat coming from to generate this? And the evolutionists don't have an answer for that. It's not discussed at all, really. It's just one of those great mysteries. But that should tell you something. If in billions of years it should have cooled off, maybe it's not billions of years old. Maybe it's just thousands of years old. And in thousands of years, it couldn't have lost most of its heat coming out of this. So it can't be primordial. And again, it's a mystery. I've never really read any serious suggestion as to what's driving it and keeping it warm, those planets so warm. Of course, if they happen to be young, then that's not a problem at all. So I think, again, this is an evidence for recent origin. And then we have the planets of the rings of the planets, and it's interesting, those rings and what they do for us. This is Uranus, not showing the rings. Here's a close-up of, I believe, Uranus's rings. Saturn has this big, broad ring system, very recognizable. It's made up of billions of untold numbers of little faint, small particles, sand-sized, microscopic, up to maybe small boulders and such. Those rings, the width on either side is tens of thousands of miles. The Earth would be much smaller. Well, Saturn's about 10 times the size of the Earth. So you can see the width of the rings is actually two or three Earth diameters. Yet the ring thickness is only about maybe 100 meters max. It's very, very thin. And you can see things through it. You can actually see the planet shining through it. You can see when the Saturn passes in front of a star, it blocks out the light, but you can still see some of the light. You can still see the light shining, the stars shining through those rings. So there's a lot not there, actually. You're seeing it by reflected sunlight. Now, as it turns out, the other planets, Jovian planets, have ring systems. You don't really see the others, but again, here's one very special image taken by the Voyager space probe back in 1986 of Uranus. The planet's off to the right. It's a very grainy photo, but you see those little rings, you see the ringlets you see there? Those are little rings that we have, they're ringlets, basically. Saturn has broad rings with a bunch of small gaps. And the other three planets have just the opposite. They have very narrow ringlets with large gaps between them. Interesting. Well, the ring particles are being moved around. There are a lot of satellites orbiting around, and they actually are yanking on those ring particles all the time, moving them up, moving them down. They have other particles coming in, like meteoroids coming in and colliding with them and knocking them out. They splash out and dissipate. And people have, we've done observations now with the Cassini probe around Saturn, and we've seen gross changes in the ring system, and people have tried to get a handle on how long ring systems can last. And they don't last very long, as it turns out. All 4 of the Jovian planets have ring systems, but they're falling apart very quickly, and people have run the estimates. They cannot be billions of years old. In fact, now they're thinking ring systems last at most 1 million years. You get a ring system, and it's gone within 1 million years. They very quickly dissipate. And these rings supposedly occur when one of the satellites or some other bodies gets pulled very close to the planet within what they call the Roche limit, and the tidal force of the planet will disrupt an object held together by gravity if it comes within that limit. You smash it apart, it becomes a ring system, and then these erosion processes go to work on it and dissipate it, and it's gone. And the question is, if the solar system is billions of years old, why is it that we happen to be living at a time when all 4 of the Jovian planets have recently destroyed a satellite or some other object to become a ring system? And just how many satellites did they have to start with? Because it should have been going on continually and continually. I don't think this is very probable at all. I think it's really indicates that the rings were probably created not very long ago, if not during creation week, certainly thereafter. And we're not seeing billions of years here, but instead, we're probably seeing evidence again of recent origin. Rings in themselves don't indicate that the solar system is young. It simply tells us the rings are young. But again, what's the probability we're living at a time when all 4 planets, Jovian planets, have ring systems? I talked about comets briefly yesterday. Yeah, I mentioned this photograph of Hale-Bopp. The nucleus is down in the lower left, and when it comes close to the sun once each orbit, the ice is sublimed into gases. They dislodge dust. Both are pushed away from the sun very efficiently. And then this thing retreats to the outer parts of the solar system, where it remains for a long period of time. It comes back in and does it again, and it comes back out and does it again. And each time it comes in, it loses a tremendous amount of material. Each time it comes in, it loses a tremendous amount of material. And so this means that comets have fairly short lifetimes. A couple of processes going on. First of all, there's evaporation, or I should say sublimation, as these ices are lost and the dust particles are lost from the comets. Then they're not replaced, and consequently you sputter and lose a lot of volatiles to power this. There have been historical comets that we have records going back centuries that indicate this falling apart process. Halley's Comet, one of the most famous comets, is not as bright as it used to be, largely because of this loss of material. Other comets, Encke's Comet's not as bright as it used to be. Every comet we see coming back periodically, we can actually track them getting fainter and fainter. And it leads to optimistic assumptions or conclusions that a comet may survive 100 trips around the sun, but no more than that, probably less than that. So comets are burning out fairly quickly. Also, there are collisions that take place. These things can come close to planets, and when they do, they can collide. The gravity of the larger planets can certainly accentuate that fact, and we always knew that that was a possibility, but before 1994, we had never witnessed it. In 1994, one comet called Shoemaker-Levy 9 actually collided with Jupiter. It was shredded apart 2 years before when it came into the inner solar system as it passed close to Jupiter, and then it came back out. As it did, it passed close to Jupiter again, but this time Jupiter was standing in the way, and over a period of several days, piece by piece, what was left of this comet smashed into it, left these big black eyes. I had a small telescope at home. I set it in my backyard, and I could see these things. They lasted a few days, and then they dissipated. So Jupiter was no worse off for the wear, but comet Shoemaker-Levy 9 doesn't exist anymore. It's gone. It's gone, never to be seen again. So we have collisions that can knock them out. And so we have evaporation, collisions, and also we have ejections from the solar system. Again, they can come close to the major planets such as Jupiter. The gravity can do one of two things. It can shorten the orbit, making it coming back more frequently, which then accentuates the other two processes coming in. And then the other thing that can happen, half the time, it lengthens the orbit, and it kicks these things out of the solar system. And there actually have been hundreds of small comets that have been observed being ejected from the solar system. They come in, they come close to Jupiter or Saturn, they pick up energy, and they leave the solar system on escape velocity or beyond orbit, never to come back. So we have three very efficient mechanisms. They either wear out by coming around with the sun too many times, they have collisions, which is a catastrophic loss, or they're ejected from the solar system, another catastrophic loss. And so when you do the numbers on this, you find out that after 4.5 billion years, there wouldn't be any comets at all. In fact, it's more close to like 100 million years, and comets will be gone. This seems to suggest that the solar system is not billions of years old, but perhaps no more than 100 million years, probably tens of millions of years old, and far younger than that perhaps. Again, this doesn't indicate 6,000 or 7,000 years, but it's consistent with 6,000 or 7,000 years, but it is inconsistent with something that's billions of years old. Now, astronomers have been aware of this for most of a century. They are quite well aware that this is a problem. So they try to respond to this, and they've responded by two things. One is what we call the Oort comet cloud. This was suggested by Jan Oort, a Dutch astronomer, way back in 1950. We're talking 67 years ago. That tells you how long ago this problem has been known. It had been known for a while at that point. And what Oort suggested was the solar system is surrounded by a big cloud of comet nuclei. Here's the solar system way down inside. Here are the comet nuclei out here, and they're orbiting around at great distances. So far from the sun, they stay cold all the time. How far out are they? Well, the average distance between the Earth and the sun is called the astronomical unit, or AU for short. The most distant planet, Neptune, is about 30 astronomical units out from the sun. Well, these comet nuclei in the Oort cloud would be thousands and thousands, tens of thousands of AUs. And occasionally a star passing close to the solar system or some other large body mass out there would affect the gravity of these bodies, and they would fall into the inner solar system. So occasionally new comets are interjected at the same rate that old comets are lost, and this gives rise to long period comets. In fact, when I was your age, they thought this produced all comets. By the mid-1980s, they began to realize that wouldn't work, so they dusted off another suggestion, and there's a long story here I won't go into. Contemporary, about in the same year that Oort did his suggestion, a guy named Gerard Kuiper came up with another suggestion for what we call short period comets. And this is a belief that just beyond the orbit of Neptune, out there on the fringes of the solar system, there is a kind of like a donut-shaped distribution of comet nuclei, and again, gravitational perturbations occasionally will knock those in, and they will take the place of older comets as they burn up or destroyed by the various mechanisms I already mentioned. So, I got a great quote here. This quote says, "Many scientific papers are written each year about the Oort cloud, its properties, its origin, its evolution, yet there's not yet a shred of direct evidence for its existence." Do anybody know who said that? Who wrote that? It wasn't me. It could have been me, but I didn't say it. Think of a famous astronomer about 40 years ago. Billions and billions. Anybody? Carl Sagan. How many people know who Carl Sagan was? Oh boy. I was expecting nobody under the age of 50, and I got a bunch of young people. They're either lying or they know stuff. I think they know stuff. I've been impressed this week by the stuff you folks know. Yeah, Carl Sagan was a famous planetary scientist, and he wrote this in his book, Comets, 1986. He co-wrote it with his wife. Now, that was 30 years ago, but the situation has not changed. There is no shred of evidence that the Oort cloud exists. Now stick with me here for a second. I grew up understanding the definition of science is the study of the natural world using the five senses, right? Y'all heard that definition before? Which means if you can't hear it, and you can't see it, and you can't smell it, and you can't taste it, and you can't touch it, it's not science, right? So they're telling me that this thing they've never observed is where comets come from, and it must be science because scientists talk about it. They publish scientific papers in scientific journals, right? Well, I would submit to you there's not a bit of science in it. It's all speculation. And again, just because a scientist does the speculating, it doesn't make it science, does it? Again, I could offer an opinion on art and music, but it wouldn't make it science, now would it? So I don't think this is a scientific concept at all. Thousands of papers have been written on it in ostensibly scientific journals, but if we don't actually observe it, then how can you claim that it's science? I'm not saying it doesn't exist. I'm just simply saying there's no evidence it exists. There's no evidence that the tooth fairy exists either. And I guess we could write thousands of scientific papers on her if we wanted to, couldn't we? All right. Now, I had said the same thing about the Kuiper Belt for a long time, but back in the early 90s, they started discovering objects beyond the orbit of Neptune. They started calling the Kuiper Belt. Actually, they had discovered one decades before, back in 1930. Anybody know what that object was called? Pluto, yeah. And a lot of you are too young, but I grew up, and most of my life, Pluto was a planet. That changed in 2006, right? And actually, was anybody upset about that? Okay, tell me, why do you like Pluto so much?
Space Harambe.
What? Any other reasons why you like Pluto so much? Well, at the risk of working up your ire, actually, I was in favor of demoting it years before. For 15 years, I was telling my students, we need to get rid of Pluto as a planet. So please don't hate me. I think part of the mystique was the fact that it was so far out and so distant, and we'd never visited it, and so it could be anything you want it to be. But that changed a couple of years ago. We went there with New Horizons. Did that burst any bubbles for anybody? Okay, well, nobody. Okay. We still have some diehard fans of Pluto here who want it to be a planet? Okay, you have the right to be wrong. That's fine. You can. All right. Well, they think the Pluto is just now one of the larger members of this so-called Kuiper Belt. And that's basically this asteroid belt we found beyond the orbit of Neptune. Now, there's an alternative term out there called trans-Neptunian objects, TNOs for short, and that's what I prefer to call them. I don't call them KBOs, Kuiper Belt objects. I call them TNOs because, see, KBO is laden with an interpretation here. It's trying to tell you this is where comets are coming from, short periods comets are coming from. But I think TNO is better because it's merely descriptive. You see, if you say TNO, you're practicing operational science, and if you say KBO, you're practicing historical science, evolutionary science, aren't you? Well, we have the density now of some of these. We have the density of Pluto, actually, pretty accurately. We have the density of its large satellite Charon, and the densities we have are around 2 grams per cubic centimeter. Now, we also happen to know the composition of comets pretty well. And I can take the comet's composition, and I can then calculate if Pluto and Charon, its satellite, are made of cometary material. I know what their density ought to be because I know what their composition is, if indeed they're the mother of comets. And the best I can get is 1.25 grams per cubic centimeter. I can't get any higher than that. That's it. So I think the composition is a problem here. And we're actually finding now densities of other bodies in this among the TNOs, and they're coming in at 2 as well, close to, not 1.25. So I don't think the data actually support the contention that these are the KBOs, that is the origins of short period comets. By the way, I didn't add this slide here. I had a whole talk I do on Pluto, not on the planet, but just about Pluto, okay? And that'd be kind of expensive to go there. But at any rate, what did they find on Pluto? Anyone? Well, they found the heart. What didn't they find much of? Well, they were expecting to find a bunch of craters, and they found some, but not many. As it turns out, vast regions of Pluto has very few craters on it. Now, why were they expecting to see craters? Well, it's billions of years old. It's been impacted for billions of years. And lo and behold, 2 years ago, they suddenly discovered that it has very few craters on it. And you know, they still can't explain that one. It seems to me that Pluto has a young surface. In fact, that's been the paradigm we've had for 50 years. Whenever we see a heavily cratered surface, it means it's old. And we see a fairly low cratered surface, it means it's young. It doesn't mean the object itself, it just means the surface could have been reworked. But the problem is there's no heat source in Pluto. There's no heavier elements to produce radioactive heating, and there certainly aren't any volcanoes on it. So it's a problem. Again, the same sort of problem I've mentioned before, some of the satellites of the outer planets. We have the sun, and I was trying to show the sun to people, and here you see the sun with some sunspots. Unfortunately, there aren't any sunspots right now. I was hoping we have a few this week, so it's just been pretty bad as far as that's concerned. By the way, I was showing you the sun. I'll try to do that some more, but I want to remind you, do not attempt this at home. All right, it's very dangerous looking at the sun. If you don't have the proper filters and don't know what you're doing, don't try it. I have both, so we're in good shape out there. Also for the eclipse later on this year, you can look at the sun during totality, but not before and after. And you need to be careful that you look away before totality ends. And you only got a couple of minutes there max to work with, depending on where you are. If you don't know what you're doing, you better get some help to find out. And there are places that are hosting events. One place I know of is Bob Jones University. They're on the eclipse path, and they're hosting an event on the campus. A good friend of mine, their astronomer there, Bob Hill, is the one hosting it. They've got telescopes, and they'll be able to fix you up nicely. So if you're anywhere near the campus in South Carolina, that may be a good destination to go to. You'll have some experts to help you there. All right. Anyway, according to stellar evolution theory, the sun should gradually brighten as it ages. It's a very complex interaction. If you want to know more about it, come see me and I'll tell you how this happens. But it ought to brighten up very slowly. Now, let's suppose the sun is 4.5 billion years old. Then it would have brightened by 40% since the time it first formed. Well, what about when life supposedly formed 3.5 billion years ago? Well, the sun would have brightened by 25%. What effect would that have on living things on the earth? Well, as it turns out, it would result in a 17 Celsius temperature change. 17 Celsius. The average temperature of the earth today is 15 Celsius. So what would have been the temperature of the earth 3.5 billion years ago then? It's 15 now. It was 17 degrees cooler back then. So what would it be? -2. That's Celsius. Now in real temperature, that's about 28 degrees Fahrenheit. The average temperature. What if the average temperature of the earth were 28 degrees Fahrenheit? It would be an ice ball, and it would never recover. Again, that's not what the earth looks like. And also, nobody believes the earth was ever like that. In fact, evolutionists believe the temperature of the earth has been fairly constant over billions of years with mild fluctuations back and forth. You see the problem here? If the sun is 4.5 billion years old, it should have been much fainter in the past. And so how in the world could the earth maintain the same temperature over those billions and billions of years? Well, there is a response to this, and the response is that the atmosphere of the earth began with a lot of greenhouse gases, and those greenhouse gases held in heat when the sun was much cooler, fainter than it was today. And with time, the atmosphere gradually changed, lost those greenhouse gases so that it exactly compensated. Now, what you have are two mechanisms going on without any feedback between them. One of them is a cooling effect, one's a heating effect, and those two exactly cancel for 3.5 billion years. Do you find that very plausible? That's pretty remarkable that two unrelated events can actually totally compensate each other like this. And again, where is the evidence that this has taken place? Actually, over the past 20 years, there have been at least 3 different explanations as to why the early faint sun paradox is not a problem for 4.5 billion year old Earth. I suspect because they keep throwing out new solutions, the old ones didn't work either, and the new ones probably don't work. So I think this means that we're looking at a very young solar system. Well, I have several other arguments I would give you, but I'm running out of time. So let me just very quickly go to the end of the presentation here. And again, I encourage you to come by our table out there from Answers in Genesis. We have a fine magazine, award-winning magazine called Answers. Anybody get Answers magazine already? Very good. Well, we have, if you want to sign up, we have cards you can fill out and pay the money for a subscription for 1, 2, or 3 years. And for each year you sign up, you get a free DVD. I only brought 3 different types of DVDs, so you got to pick between those 3. But you can either get 1, 2, or 3 DVDs if you sign up for 1, 2, or 3 years. It's a great magazine. It's got a kids section inside. It's really jam-packed. It comes out 6 issues a year. We have that and many other items. So please come by and peruse what we have to offer. Thank you very much.